Until last week, I thought the best way to measure a participant is to just measure that participant. So for example, if you are interested in the true IQ of a participant, you give them an IQ test, look what comes out of that measure, and that observation is your best guess for the true IQ value. Now, at last week's ASSC, a conference on conscious processing, I was made aware of a result from a couple of, 100 years ago, from Kelley, who basically studied correlations, but from his results, something, in my opinion, quite unintuitive comes out, namely that there's a better way to measure individual true scores. So let's set up the setting. Let's call this Kelley's correction. And the idea here is that we have for each participant a true score. Let's call this TI. That's basically the true IQ value. And let's assume this comes from a normal distribution with some expected value and variance. So for example, expected value 100 and standard deviation of 15. And now we don't have access to the true value, we can only measure it. So we give them an IQ test, and we don't always get the same value from this IQ test. So we have some measurement error. Let's call this I. And let's also assume this measurement error is normally distributed with an expected value of 0. So we don't systematically over or underestimate the participants' true values. And let's call the variance here sigma E squared. And let's call this variance of the true scores sigma t. So for this true value, a participant has some measurement error, and whatever comes out is the observation x. Observation x is just xi, is just the sum of these two things, the true value plus whatever we over or underestimate this participant. And now we take a sample of multiple participants from x1 to xn, and we compute the sample mean, denote this by m as 1 over n times the sum of xi. And now the question is, can we get a better measure for ti better than xi? Xi is the individual's observation, their test score in the IQ test, and we want to get to the true IQ score ti. So can we do better than just taking xi for granted? And the spoiler here is yes, actually, in some sense, there's a better measure for this, and we will call this the corrected observation. And this is xiw, and this w is a weight, and we will basically correct our observations xi by multiplying this weight onto it, and influence the observation a little bit by the mean. So basically for each participant's IQ measure, we shift it a little bit back to the mean because we assume that's where their original value came from. And the question is now just, does it make sense to have a W that actually shifts them, and how far should we shift them? So for example, if the W is 1, we would not shift at all because we take 1 times the original value xi plus 1 minus 1, so 0 times the mean, so that would be no shift. W of 1 would be no shift. But does it make sense to use some shift at all? And we also have to define in what sense do we want to evaluate these things. And let's just say we take the relatively common mean squared error, MSE, which basically looks at the sum of the squared difference between the value that we estimate, our corrected observation, minus the value we want to estimate, the true scores TI, and square this difference, take the sum. Now, the idea is that we basically say, how does this mean squared error change if we change the W? The idea here would be that we have different W values, and if we plot the mean squared error for these different W values, we will get a curve like this. I will not go into the proof, but there is indeed a value W that is smaller than 1, but larger than 0, for which this mean squared error is minimal, optimal. less error. And we will not go into the nitty-gritty details. You will basically just have to take the derivative here, make reformulations. But what turns out is that if you force this value to be 0, and that will be the case at this minimum value here, where the slope basically becomes 0, it changes from underestimating to overestimating, or it changes from making mean squared error because we shift too much to the mean squared error where we shift too little. There's an optimal W, and that turns out to be something like the variance of the true scores divided by the variance of the true scores plus the variance of these epsilons, which is also known usually as the reliability. So the reliability would be if you do the same IQ test again for all of the participants and you take the correlation between these values. The correlation would indicate how consistent, how reliable are the individual values measured. That will be the value that we have to use for our correction. Basically, if our measure is very, very reliable, we mostly just take the observed value we have. But if our measure is relatively unreliable, we take to a big part the mean of our group into the estimation, into the corrected observation. And interestingly, this will give us a better mean squared error, which I did not think is possible. But you have to be careful. If you then take these corrected observations, their deviations, their errors will not be independent anymore of the true score. Usually we set something like the errors that you have will be independent of the true scores, meaning that if a participant has a relatively high true IQ, the measurement, the IQ test over or underestimates with independently of how large this true IQ score is. However, if we basically say that we have these corrected observations, their deviations from the true score will not be independent anymore of their actual values. Basically, because we, if we have a very large observation, we corrected relatively much in comparison to small, to like observations that are close to the mean, they will only be shifted a little bit. And these differences of shifts, they will introduce some dependency. So while this holds the basically measurement error that you could define based on these W's. I will not go into the details, but just to have it kind of here is not independent anymore, and you have to be careful of that. But other than this technical problem for further inferences, we have a way to reduce the mean squared error. We have a better way to measure the individual values, true IQ scores, if we consider the reliability of this measure and weight it with the actual mean of the sample.